Hello, welcome to a video about X-rays. X-ray photons can be produced when electrons that have been accelerated to high speed interact with a target. This is done in a simple X-ray tube. The three main features of the spectrum of X-rays produced in this way are a continuous range of frequencies, and this is called Bremsstrahlung, I think is how you pronounce it. A maximum frequency is given by Fmax equals the charge on an electron multiplied by the potential difference divided by Planck's constant. And the last of the main features is that high intensity peaks at particular frequencies, known as characteristic X-rays, occur in this spectrum of X-rays produced. In stage 2 physics, you'll need to be able to describe the purpose of the following features of a simple X-ray tube: the filament, target, high voltage supply, evacuated tube, and a means of cooling the target. You'll also need to be able to sketch the graph of the spectrum from an X-ray tube, showing the three main features of the spectrum. You need to be able to explain the continuous range of frequencies and the maximum frequency in the spectrum of the X-rays. You also need to be able to derive the formula for maximum frequency, and you need to be able to solve problems involving the use of this formula. So the generation of X-rays is essentially a reversal of the photoelectric effect. So bombarding a metal target with electrons essentially leads to the generation of photons. And this is the principle behind X-ray production. And the image that we have in this slide is of an X-ray tube. We'll look at this in closer detail on the next slide. So just to reiterate, X-rays are produced by accelerating electrons to high speeds and then colliding them with a target. So the purpose of this target is to be hit by these electrons, so then photons will then be generated. The electrons are generated and emitted in the first place by heating a wire filament of a cathode with an electric current. So in our diagram here, this zigzaggy part here would be the filament, and this is what's heated to then emit electrons, and this emission is called thermionic emission. The emitted electrons are accelerated to a positive target anode, so the target is a positive anode. Obviously, anodes are usually negative, as we touched on in the photoelectric video, but they are induced to be positive in an X-ray tube, and the electrons are accelerated with a large potential difference, and this is produced by a high voltage power supply. So the purpose of the high voltage power supply is to produce this large potential difference. High speed electrons then collide with the target, and this converts kinetic energy, so the kinetic energy that these high speed electrons have, that gets converted to mostly heat, but it also gets converted to X-rays. I think X-ray production is quite inefficient, so it's only like 1 or 2% of energy is converted to X-rays. Most is, lost or converted to heat, and this heat is dissipated via cooling fins, which in this schematic here are made of copper rods, or alternatively the whole anode can rotate. So both of these options dissipate the heat. In this diagram we've just got copper rods. So those copper rods will conduct the heat away from the target. All of this is housed in an evacuated tube, and the reason the tube has to be evacuated is that electrons don't collide with other molecules and therefore lose their kinetic energy or their velocity or change direction. So there has to be just completely empty space, so no air molecules or anything in the tube, or molecules that make up air in the tube. Otherwise, electrons would lose their full kinetic energy. And as a further result, X-rays may not be produced because those electrons do need to have a really high speed when they're hitting the target anode. So now we'll take a look at the X-ray spectrum produced, and this is continuous due to the lots of different interactions of electrons with the target anode. So the target is usually made or comprised of atoms with a high atomic number, so a heavy metal, with a high positive charge on their nuclei, so lots of protons in the nuclei. Electrons that are incoming will decelerate, change direction, or collide with the nuclei, and this is a result of bremsstrahlung, which is called breaking radiation, which that's like the direct translation. Essentially what happens is electrons will be incoming, and if they either decelerate, change direction, or collide with the nucleus, they'll lose a bit of kinetic energy, and this leaves the electron in the form of an X-ray photon. So the kinetic energy that the electron did have is converted to a photon. So the change in kinetic energy that that electron experiences is going to be equal to the energy that the X-ray that it's converted to has, and that is going to be equal to Planck's constant multiplied by the frequency of the X-ray, because we know that energy of a photon is equal to Planck's constant multiplied by a frequency of the photon. So if it's an X-ray, it's the same, it's just an X-ray photon. So the energy of the X-ray is going to be equal to the Planck's constant multiplied by the frequency of the X-ray. An electron that travels at a lesser distance from the nucleus is going to experience a greater deceleration. Therefore, the photon that is released will have a greater energy, and that will correspond with a higher frequency. So, because the attraction force is stronger, as the electron is closer to those positive charges, it'll lose more energy. Therefore, the X-ray photon that's emitted will have a higher energy and therefore have a higher frequency. So this, because we're talking about electrons decelerating, changing direction, and colliding, these three options make up the entire spectrum of bremsstrahlung. So that is what this whole part of the graph is, I guess, depicting. So any energy that occurs as a result of an electron's motion changing. The other two features of the X-ray spectrum that you'll have to know about are the maximum photon energy and the characteristic radiation, or the characteristic peaks. So the maximum photon energy, or the maximum photon frequency, is produced by an electron's collision with the nucleus. So in this situation here, if an electron collides with a nucleus, then all of its kinetic energy is going to be converted to a high energy or maximum energy photon, and that's because it's collided with the nucleus. The electron is completely stopped, therefore all of its energy gets converted to an X-ray photon. The characteristic peaks are produced, which are these sharp points here. They're produced by or as a result of electrons colliding, so the incoming electrons colliding with the inner shell electrons. So what happens here is when those electrons collide, the incoming electron knocks the inner shell electron out of position, And as you may have touched on in some previous chemistry somewhere along the way, or maybe not, electrons will jump down energy levels because they want to be in their most stable, position in an atom, and that's generally closer to the nucleus. So once that inner shell has been knocked out of place, an electron that's further out will move down energy levels in the whole atom, moving closer to the nucleus to fill that vacancy that has formed. And as it's moving down those energy levels, or that energy level, it'll emit a photon of energy. The electron that fills the vacancy isn't always going to be the same electron, so the peak that is produced as a result of this isn't always going to be the same. So that's why you might have a number of different characteristic peaks in your X-ray spectrum. One thing that I'll just mention is that all electrons enter the target with the same kinetic energy, and that's because of the potential difference that they're accelerated through. So upon entry, these electrons that are being fired into an atom will all have the same kinetic energy. So they're being fired into the target anode. They all have the same kinetic energy to begin with, and how much of this is converted into X-ray photons varies depending on what each electron experiences. The maximum frequency, or Fmax, is produced by an electron that collides with the nucleus, so when all of that kinetic energy is converted to a photon, as we just touched on in the previous slide. This maximum frequency is dependent on the potential difference between the cathode and the anode, so the voltage across the cathode and the anode. The electron energy from the potential difference, which is also known as the work, so the work that potential difference has done on the electron, is equal to its change in energy, so how much its energy increases, which is the charge multiplied by the potential difference. We know that this change in energy, or the work done on the electron, is going to be entirely converted to the energy of a photon, because we're talking about the maximum frequency here, so when the electron collides with the nucleus. So that energy from the potential difference, or change in energy, is also going to be equal to Planck's constant multiplied by the max frequency, which is the photon energy. And that's going to be equal to charge multiplied by potential difference, which will be also equal to the, or in this situation, equal to the charge on an electron multiplied by the potential difference between the cathode and the anode. If we want to rearrange that entire equation, so if we're just looking at Planck's constant multiplied by max frequency being equal to the charge on an electron multiplied by the potential difference, we can then rearrange that to get an equation for the maximum frequency of the photon, the X-ray photons that is released. So you're just going to be dividing both sides by Planck's constant over here. So if we've got a potential difference of 4.00 by 10 to the 4 volts, and that's applied across an X-ray tube, what is the kinetic energy of the electron? or any electron, and what is the maximum frequency. So to work out the kinetic energy, we know that EK, kinetic energy, is equal to an electron, charge on an electron multiplied by the potential difference, and this will just be 1.6 by 10 to the negative 19 multiplied by 4.00 by 10 to the 4 volts, and this is going to be equal to 6.4 by 10 to the negative 15 joules. So that's our kinetic energy of the electron. Now we need to work out what is the maximum frequency. So Fmax is just going to be equal to E, or charge on an electron multiplied by the potential difference divided by Planck's constant, and this incidentally is going to be equal to the kinetic energy divided by Planck's constant, so this will be equal to 6.4 by 10 to the negative 15 divided by 6.63 by 10 to the negative 34. So 6.4 by 10 to the negative 15 joules divided by 6.63 by 10 to the negative 34 joule seconds, and this is going to end up being 9.65 by 10 to the 18 hertz. So that is the maximum frequency, 9.65 by 10 to the 18 hertz. So that's the maximum frequency that an electron can have if the potential difference is 4.0 by 10 to the 4 volts. So X-ray images are produced by irradiating objects with X-rays with a photograph plate behind. So images are produced by differential absorption or scattering of photons. So in our, I've just got a schematic diagram of how a setup looks. So we've got an X-ray tube, I suppose, it's producing X-rays, and they'll be fired at whatever is being X-rayed, and then there'll be a detector on the back. So where the white parts of the image are means that the X-rays have been deflected or absorbed or scattered more than where the darker parts of the X-ray are. So where there's darker parts, it means that X-rays have just gone straight through. So like sort of like the tissue and fleshier parts, there's more X-rays that have gone through compared to where the bones are. So bones are more likely to scatter X-rays, and that's why we get a nice image of our bones in X-rays. Attenuation is the reduction in X-ray intensity due to the absorption and scattering of X-ray photons. So bone is going to attenuate X-rays more. This is dependent on material thickness, material density, and the atomic number of constituent elements. So if we think about our flesh, it's generally made up of carbon, hydrogen, oxygen, maybe a bit of nitrogen, and all of those atomic numbers are reasonably low, whereas our bones have a lot of calcium in them, and the atomic number of calcium is much higher than those other elements. So the atomic number, or the higher atomic number, results in greater attenuation because there's like more, the nuclei of those atoms are bigger. The attenuation coefficient, which is represented by mu, which is the U with like a tail, is measured in per meters, and it's the degree of X-ray absorption or scattering, which is dependent on density and average atomic number. So the larger the difference in attenuation coefficient between materials, the more increased the contrast in an X-ray image will be. If you look on page 355 of your workbook, you've got the attenuation coefficient for a load of different tissue types. And you'll see that for bone, the attenuation coefficient is much higher than it is for other tissue types. The hardness of X-rays refers to the penetrating power of X-ray photons, and this is proportional to the energy and frequency of photons, and then of course the potential difference that is used to produce these X-ray photons. And hopefully you can see that this makes sense, because if we've got maximum frequency being equal to the charge on an electron multiplied by the potential difference divided by Planck's constant. The charge on an electron and Planck's constant are both constants, so they're not going to change. And hopefully you can see that the potential difference is directly proportional to the maximum frequency. So if the potential difference increases, then the maximum frequency is going to decrease, and vice versa. If the potential difference decreases, the max frequency will also decrease, so they're directly proportional to each other. X-rays that are hard are high penetrating, and they consist of high energy photons, so they're generated with a large potential difference, and this type of X-ray is used for chest X-rays, leg X-rays, and airport security. For softer X-rays, these are lower penetrating, and they're generated with low energy photons, or they consist of low energy photons and are generated with a lower potential difference. These are useful in mammograms, X-ray microscopy, and in some research as well. The exposure time is how long a person or object is exposed to an X-ray or exposed to X-rays, and this can be minimized by increasing the X-ray intensity, by increasing the potential difference across the filament, and therefore increasing the filament current, so increasing as a result the thermionic emission of electrons, which then bombard the target anode and hence produce more X-rays. So the rate of production and emission of X-rays is increased. X-rays are an ionizing radiation that can damage tissue by causing mutations in DNA, and the risk of damage is dependent on the hardness and intensity of X-rays, as well as the exposure time. So exposure time can be reduced by increasing X-ray intensity. However, increasing the intensity also increases potential damage to tissues, because each X-ray photon has the potential to ionize one or more molecules in cells. So managing the risks of X-rays involves compromising between all of these factors and what's going to, I guess, be the best overall exposure, or the best overall intensity, or the best, hardness for what you need to be able to see and achieve with your X-rays, but also trying as much as possible to minimise whatever the exposure time has to be by varying those factors.